Howdy everyone, welcome back. Today we're going to be continuing our analysis of magnetic fields and electrical currents and how they interact and so on. Specifically today we're going to be looking at the idea of how you can apply the right-hand rule for conventional current to how magnetic fields are generated by these moving electrical charges. Now, if you haven't yet, before you watch the rest of this video, make sure you go back and watch the videos previous to this one, which are the PSSC Magnet Lab video. Definitely watch that one if you haven't yet. There's also a couple of other videos on how you can see how solenoid coils generate a magnetic field. Okay, so specifically here, just want to remind you that, remember, everything we've seen up until this point has shown us that there's this very curious interaction or duality between electrical phenomena and magnetic phenomena. As you saw previously, you saw when you have an electrical charge that moves through a magnetic field, and it doesn't matter if it's a freely moving charge or if it's a charge that is confined to a wire like an electrical current, you'll notice that you get these forces of interaction, and the only way we can really describe them accurately is to use the right-hand rule for positive charge, the left-hand rule for negative charge. Okay. So now what we're going to do is we're going to apply these ideas to how you can describe magnetic fields generated by electrical currents. Okay, and remember, when we talk about electrical currents, because this is AP physics, we're talking about electrical currents in the context of conventional current, that is positive charge flow. So we're going to use our right hand. Okay, so suppose that what you have is you have a conventional current moving through a straight wire like this. Okay, so let's suppose that what we've got is an electrical current that is going in this direction that I'm pointing with my finger. All right, and we want to describe the magnetic field generated in the space around this wire. Okay, now, like if you've seen the previous videos, you know that there will be an there will be a magnetic field that is generated around the wire, and that this magnetic field circles around the wire, right? So if you've got the wire like this, then the magnetic field will circulate one way or the other around the wire like that. Now, how do you figure this out? Which way is it? This is where the right-hand rule comes in. Okay, so what I'll do is I'll use this red pen as a visual aid. Okay, if you envision the red cap here, think about the red cap as being the indicating the direction in which the current is flowing, right? So it's going that way. Then what you do is you use a very similar variation of the right-hand rule that we've done before. What you do is you take your right hand and you put your hand in what I call the Hitch-Hiker position. Okay, so as you stick your thumb out, you wrap your fingers like this, and like you're hitchhiking, and you stick your thumb in the direction of the current flow, the conventional current flow. So if the conventional current is going that way, okay, then what I do is I stick my thumb in that same direction, like so, right? You can see that. And then my fingers, you notice, in order to grip the wire, my fingers have to wrap around like this. So what that tells you is that the magnetic field is wrapping in the same direction as my fingers are going. Now, if you flip the current around like this, for example, okay, then you can see that my fingers also flip, right? So the magnetic field was going one way around the wire previously, now it's going the opposite direction because I flipped the direction of the current. So let's work through a couple of quick visual examples over here on the board so that you can get a better idea of how to think about this. Because there's usually a few different ways that this is written down. And for the purposes of these illustrations, I'll draw all the currents in terms of this red marker color, and then I'll use a different color for the generated magnetic field. Okay, so for the examples that we just looked at with the wire, let's suppose that what you have is you've got a conventional current going through a wire in this direction. Okay, according to our modified right-hand rule, what you're going to do, hitchhiker symbol, right? You stick your thumb in the direction of this current, and you'll notice that your fingers wrap around in such a manner that on the bottom they point into the board, and on the top they point out of the board. Okay, so the magnetic field will circle around like this. So to indicate that, what we do is, remember the symbol for going into the board is a circle with an X, and the symbol for coming out of the board is a circle with a dot. So going into the board on the bottom, we would say this. And coming out of the board on the top, we would say this. Now, of course, if you flip, so again, that, right, fingers come out on the top, go in on the bottom. If you flip the direction of the current, of course, this will also reverse the magnetic field. So suppose what we do is we have the current going this way now. Okay, you will see, let me get on this side. Okay, you will see in this case that if I stick my right thumb in this direction, my fingers on the top poke in, and on the bottom poke out as my fingers wrap around. Okay, so you reverse the direction of the current, you're going to reverse the direction of the magnetic field that the current generates. So you'll see something like this. Okay. Now, of course, there's all kinds of different ways to orient this, right? We could say take our hypothetical current, instead of having it go, one to the right or the left like this, right? Like we showed over here on the board. You could have scenarios where, say, the current is either coming out towards you or going inwards away from you like this. And in that case, you use the same configuration of your right hand. You just stick your thumb one way or the other, right? So if the current's coming out towards you, you stick your right thumb this way, and your fingers wrap around in this direction, okay? And I believe from your vantage point, that is a counterclockwise direction. And if you flip it over so that the current is moving away from you, then your fingers wrap in the opposite direction. And if they wrap this way, then of course, from your vantage point, that is a clockwise rotation. Okay, so what those would look like is the following, right? To start off with the current coming out of the board towards you. And this will lead to a counterclockwise magnetic field generated. That magnetic field will, as you've seen in the videos, right, this magnetic field will wrap around the wire in a circle like this. And if you flip the direction of the current through the wire like this, then you get a clockwise magnetic field generated. Okay, now these are scenarios of a situation where you have a straight wire, right? Where you have this wire nice and straight, okay, and the current's going in a very specific direction and so on. But of course, if you start to change the geometry of how the current is moving through the wire, that also changes the geometry of the magnetic field. And one of the most specific situations that we look at in magnetism is if you take a wire like this and you start to make loops out of it, right? So instead of having it straight, you start to kind of loop it around onto itself like this. Okay, and if you do that, then what will happen is if you only have a few loops, right, you get something that looks like this. But if you think about doing this like many hundreds of times, right, you do this hundreds and hundreds of times, and you keep looping and looping and looping and looping, what you basically get is you basically get this like long cylindrical set of loops of wires, and that's what's called a solenoid coil. And solenoids are extremely important for reasons I'll mention in a few moments. But in this situation, in order to talk about the magnetic field that's generated by the current running one way or the other way around the wire loops, we have to use a different variation of the right-hand rule. So let me erase these right here, and then I'll show you what I mean. Okay, so the variation of the right-hand rule that you have to use in this case is you still have your right hand in the hitchhiker position, right? Thumb sticking straight out, fingers wrapping around like this. But the fingers and the thumb swap roles. Before, when the wire was straight, the thumb represented the direction of the current, and the fingers represented, whichever way the fingers curled, represented the direction of the magnetic field. Now, when you start to loop it around like this, they switch roles. So now your fingers represent the direction of the current, and your thumb indicates the direction of the magnetic field. This part's important. The thumb indicates the direction of the magnetic field inside the loop or inside the coil. Okay, and I'll mention why that's an important distinction in a moment, right? So for example, if we have this loop of wire like this, and if from your vantage point you take your right-hand rule and you wrap your fingers around this way, this indicates that the current is going around in a counterclockwise direction, right? Then from your vantage point, you would see the magnetic field in here poking out towards you, right? Like this, all right? And we would draw that in the following manner. Okay, so you have this current going around this way, counterclockwise. So this supposes you're looking at the end of the loop, right? You're at the end of it and you're looking end on. Okay, so you've got a current going like so. And then according to our modified right-hand rule, the magnetic field here is on the inside is poking out towards you. So you get something like this. Now I'm being very careful here to talk about the magnetic field on the inside of the coil, because in the videos that you've seen previous to this one, you may have noticed that that there exists a magnetic field exterior on the outside here, but it's in the opposite direction. Right? Again, if you haven't seen those videos, go back and look, and you'll see that the direction of the magnetic field on the inside of the coils is the opposite of the magnetic field on the outside of the coils. In fact, the magnetic field of a solenoid coil looks very much like that of a bar magnet. Okay, so what we do to indicate that is here on the inside we have the magnetic field coming out towards you, but on the exterior region here we'll say it's going the opposite way, because that magnetic field has to come out and then wrap around this way to circulate all the way around through the coil. And of course, like we saw before, if you have a coil of wire like this and you reverse the direction of the magnetic field, right? So up until now we were talking about the current going this way, magnetic field comes out toward you. If you flip your hand over, so now you've reversed the direction of the current, so that from your viewpoint the current is now going in a clockwise direction, the magnetic field inside is away from you. And so it looks like this. Okay, right-hand rule, and that will generate your magnetic field going inwards. But again, that's only on the inside of the coils. In this exterior region, of course, the magnetic field will flip around just like you've observed in the previous videos. Okay, so this is how we use a modification of the right-hand rule to predict and describe the direction of magnetic fields that are generated when you pass current through wires. Okay. Now, I mentioned to you before the importance of solenoids, right? Remember, a solenoid is like if you have a bunch of loops of wire and you kind of make a nice long cylinder out of that. Solenoids are very common when you talk about magnetic magnetic fields, and the reason why is because it ends up, for reasons that you'll see later after we study some more about what's called Ampere's law, it ends up that the magnetic field that's generated on the inside of a solenoid coil is, for all practical purposes, uniform, right? It's pointing in the same direction and constant magnitude. So solenoid coils are for magnetism what parallel plates are for electric fields. And like I said, after we get through a couple more things, for example, studying the law of Biot-Savart, then we'll get to Ampere's law. And once you study Ampere's law, you'll understand why that's the case. Okay, so if you have any questions, let us know on the discussion board. Otherwise, we'll catch you next time. Take care, stay safe, go Team Physics.